Yes, so recording has started. So good morning once again to all of you. So in the last class, we were discussing about, we have discussed about this different numbering systems when their conversion techniques, right? How to convert from hexadecimal to decimal, decimal to hexadecimal, then decimal to binary, binary to decimal, hexadecimal to binary, binary to hexadecimal, right? Octal to binary, and all these type of conversions that we have discussed already in the last class. And towards at the end, we have also started discussion on this digital logic gates, right? So here we can see there are the couple of, you also already know that there are like AND gates, OR gates, NOT gates, then XOR gate, NAND gate, right? Different types of gates are there, and we will discuss them game okay slowly as we move on today in today's class. So here we have discussed about this AND gate yesterday, and the the AND gate generally the AND operation is being denoted by this dot symbol. So it is this X dot Y means X and Y. Sometimes this dot is also not been given in between. So it is X. If this is like X and then Y, then it means this it is basically an AND operation between X and Y. Right, and we have already mentioned that the parameters is only been given by an or any input has been only been denoted in digital electronics by a single alphabet. It may be an uppercase alphabet, or it may be an like A, B, C, D like this, or it may be also an lowercase alphabets. Right, that is also fine. So any one of them you can use. Huh? And the symbol, the circuit symbol of this AND gate is like this. This is basically a two input AND gate. So like that, you could have this three input AND gate as well, right? So three input means that there are three inputs and one output. Output is always going to be the one, right? For this case. And for this two input AND gate, we have also discussed about the truth table, right? Truth table is basically is a table which shows the output for different combinations of input. So you can see there are two inputs. So all four possible combinations of inputs has been given, and for each of the input sets of X and Y, what will be the output that is also been denoted. Similarly, you could have three input three input and right, then for that what will happen, for that you have to make it X, Y, Z, and then it is F, right? So like that there are three variables, so the total number of this combination that would be 2 to the power 3, right? So there would be then 8 different combinations, right? Like for example, it will start from 001, 000, 001, 010, 011, 100, 101, 110, 111. So you can see there are 1, 2, 3, 4, 5, 6, 7, 8. So 8 different combination, and for 8 different combination, what will be the output? So let us do that quickly. So this is AND gate. So for AND gate, output would be 1 only when all the inputs are equal to 1. So for this only output would be 1. For all of them, the output would be 0. Right? So this would be the truth table for this 3 input, for this 3 input AND gate. Right, and we have also discussed about this, that this is a type of equivalent you can think of this AND gate. This AND gate is basically and like two input AND gate. Basically, there are two switches, and this is connected with a battery, and this is a bulb, right? And so when both the switches are actually in the on position, means both the switches are on, then only the light can glow. Right? So that means if both the like if you can see it here, if both the inputs are only one, that one denotes here the switch is on, right? Then only the output will be one. Otherwise, the output would be zero. Right? Okay. So let us then start or discuss the other gates as well. So here we will take some speed, huh? And please feel free to ask if you have any difficulty in understanding at any place. So the number two is OR gate. Okay, so this OR gate is basically, suppose if you are doing a two input OR gate, and it's basically denoted in this way, huh? This X plus Y. This plus is basically the OR operation. Okay, and the circuit symbol of this OR gate is like this. So it is XY, it is x plus y. So plus means it is not the addition. Remember that it is the OR operation. Huh? Here. And then what will be the truth table for this OR gate? So OR gate, so it is basically F. F is the output. So OR gate, it is like its operation is like this. When or operation, right? You know that. So or operation means when at least one of the input is 1, then the output is going to be 1. So here both inputs are 0, so output is going to be 0. Here one of the input is at least 1, so the output will be 1, 1. Here both inputs are 1, so still it will be 1. So the condition is at least one of the input has to be 1 for the output to be equal to 1. Right. So similar to the circuit equivalent that we have seen in the last class. So you can think of like two switches which are connected in parallel, and like this is that light, and it is this battery, right? Right. When any one of the switch, like when any one of the switch is like in a on position, then the light will glow, right? Either this or maybe both, right? Right. So either like at least one of the switch has to be on. If both of the switches are also on, then also output would be 1. Right? So this is the truth table for this OR gate. Okay. Then the third one, that is this NOT gate, right? So for NOT, the circuit symbol of this NOT gate is like this, right? So here, if it is X, it is denoted as X bar, or you can sometimes also denote it as this X dash. Like you can use either this or this or this. And the truth table corresponding to this would be, so again, F means output, okay, everywhere. So when like here for NOT gate there is only one input, so and the output would be inverted. So if it is 0, it would be 1. If it is 1, it would be 0. Okay. Number 4 is buffer. So buffer, actually we already know, but we know in terms of this our previous study. For detail also, it would be the same. So whatever you give, right, you will get it at this output. So the truth table of this 0 to 0, if input is 1, it would be 1. So that is basically the buffer. Then this NAND.
Sir,
Huh.
sir,
Yes.
if we get exactly the same output in the buffer, then why using this device? I
Hey,
mean,
why we have discussed it couple of times because of this, impedance, right? Here the impedance is here much like higher for analog point of view, and for digital point of view, if some signal, current supply is quite weak. Okay, so suppose like how many gates you can attach. Okay, maybe I will take your question just after finishing this part. Okay, so there is an current driving capability which is called also the fan out. So if some different gates has some limitation on its fan out, so from that point of view, many times we use an buffer. So I will take this point just after finishing these gates. Huh? So this NAND gate is like this X Y, and this output is F, right? So all are like two input, device, two input like gates. So you could have more than two inputs as well, huh? So AND operation is basically it is AND means it is equivalent to this AND gate followed by a NOT gate, right? It is basically an AND gate followed by a non inverter, right? So for AND gate what will happen here? The output would be 1 only when both the inputs are 1, right? And for remaining cases, output would be 0. But then you have an inverter. So inverter will it will just again invert, right? So what it will does, that means for AND gate, for all these three, the output would be 0. Or only for this, it would be 1. So now we have inverter after that. So all this would be now 1. And when it is 1, 1, the output would become 0. Is that clear to you? NAND gate?
yes, sir.
Okay. Then NOT gate. NOT
Sir,
gate. Huh.
this NOT gate is You're calling it inverter. This is not the inverter as op amp, right?
This is not the inverter. And in op amp, which inverter you are referring to?
Inverting circuit.
Inverting amplifier, no, that is not inverter. That is not inverter, right? That is inverting amplifier, right? Inverter means, in the basic your circuit operations for BJT we have shown like this, no? Suppose this simple circuit will act as a type of inverter. When the input is high, right, this transistor is on, then here the output would be very low, around 0.2 volt, right? So when this is 5 volt, so this is 0 volt. This is around 0.2 volt. When this is at this base voltage is 0 volt, the output would become 5 volt because transistor is off. Okay,
Yes.
so this is actually an inverter circuit, not that op amp.
Yes.
This is a basic inverter actually. We do not use this inverter in digital circuits. So this is again a NOT gate. Again, you can think of NOT gate as like OR followed by NOT, right? So that way you can quickly again write its truth table 0 0 0 1 1 0 1 1. So for OR gate, it is like any input 1, the output would be 1, right? Now after that we have a NOT gate. So that means for all these cases, where all three cases, here, here and here, where the output used to be 1 for OR gate, now here the output would be 0 0 0. And for this 1 0 0 case where the output used to be 0 for OR gate, now here the output would be 1. Is this clear to you? Okay.
Yes, sir.
Then we have exclusive OR. Exclusive OR, also sometimes written as XOR, right? Exclusive or XOR gate, huh? And it is denoted by this circuit symbol. It is XY and it is F, and its representation is like this. Okay, XOR plus surrounded by this circle. Okay, so and what will be the truth table of this XOR? The XOR is like this. When both the inputs are same, okay, when both the inputs are same, then the output would be 0. So here both inputs are same, output would be equal to 0. When both the inputs are same, output would be equal to 0. When both the inputs are different, the output would be 1. Okay. So each this X and Y, okay, each of them are called literals. Just remember this terminology. Okay, this both X and Y, they are called literals. Then we also have another gate in this context, which is called exclusive NOR gate, or it is also written as this X NOR gate. I think for one of you, microphone is on. Could you please keep your microphone? I think Bishanathan. Bishanathan, could you keep it could you keep your microphone mute? Okay. So guys, can you hear me?
Yes, sir.
Okay. So this exclusive NOT gate is circuit symbol is like this. It is X, Y, F, and its representation in terms of this between this. How we write it? It is basically dot provided by circle. So it is X, Y to treble this output. Here, this is like when the both inputs are same, right? Both the inputs are same, then the output would be equal to 1. Right? When they are different, it would be 0. Right?
And
So
sir,
this is
how we can represent them in circuit, sir? These two gates, like the bulb and switch circuit.
these two gates.
Yes, sir.
Okay. Okay. So for that you should know how can you break this. Okay. So Can you break this thing by this x plus? Okay, before that, I have a question to you. How do you represent NOT gate? Okay, by this bulb and switch process. NOT gate.
So we can draw a switch in parallel to the bulb.
Sorry,
Switch parallel to the bulb.
switch parallel to the bulb. Okay, like this. You were trying to say like this, right? Am I correct? Are you trying to refer to this?
Yes, sir.
Okay, right. Yeah, it would work. So switch parallel. So you know how to make, then not, how to make or, and how to make and, right? Okay. Now let's see here. This exclusive OR, okay, it is x plus x or y. Can we write it some this x or something like this? Just check it out. Okay, when both inputs are different, right? Means 0, 0, 1. Say x is 0, y is 1. So x 0, y 1, right? When x 0, so okay, how to check it? Okay, so say that we are testing, okay, whether this x plus y, this x or y is equal to this expression or not, how to check it? Okay, you know the truth table, take the value, like for example, x, take this value, 0, 1. So x is 0, so keep x 0. So anything multiplied with a 0, because this is an AND operation, right? So if you do an AND operation for AND, if one of the input is 0, then this term would be become 0, right? Are you with me on this? This is an AND operation
Yes, sir.
between x and y bar, right? And here x is 0. For AND, if one of the input is 0, then the resultant would be 0. So that means this term is 0, right? Okay. Plus, let's see the second one. It is x bar y. So x bar become 1, y is already 1. So this term become 1, right? Now it is an odd operation between these two, where one of the this is 0, other one is 1, right? Odd operation is if at least one of the input is 1, then the output become 1. So it is 1 plus 0, so that means output would be 1, right? So you can see this output is expected to be 1 for this, right? If you test it for this, similarly, you will also get that output will come for 1. Now let us check it for this 1 case. So x1, fine. Y, it is also 1, but it is y bar. Y bar means 1 bar. 1 bar means it is the like it is inverse, right? So it is 1 means it becomes 0. So it is x and 0. X and 0 means this part is 0. What about this x bar y? This x bar is 1, so it becomes 0. So it is 0 and something. So if in AND operation any of the input is 0, then the output is going to be 0. So it is then 0 plus 0. 0 plus 0 means 0 or 0 is always 0, right? So the output would be 0. So see, the output is also matching. Okay. Now then if we can write this expression by this, okay, by this expression, if you can represent this x or y by this, and here you can see this is basically broken down to very simple operator, very simple operation. It is this AND operation, NOT operation, here also and NOT operation, right? So if you know how to represent these basic gates by this circuit, by this switch and this bulb, this representation, so I hope it would not be difficult for you to represent this exclusive OR. Is this clear to you?
Yes, sir.
Okay, just a minute. So here, after that, so you have understood, right? And how to cross check also. This will again, we will do it today. So let us then go to the next page and see a couple of things here. So the first one we will learn here is called this Boolean algebra. Okay, so this Bully was the name of that person. Okay, from this name only, this Boolean algebra, this term has been derived. Okay, so this Boolean algebra we use typically for minimizing, huh? Minimizing an expression, which minimizing an expression consisting of different literals. Okay, maybe before that I will ask you one more thing. Okay, suppose we need to design a function which consists of this xy, okay, plus z. Hmm. Xy plus z, or say plus xy plus say xz. Okay, xz. How you are going to do it? Can you do it? This is a function which is xy plus xz. So here x is one input, right? Y is the other input, second input. Z is the third input. How can you do it?
Sir, we can take the or between y and z and then end it
Right.
with x.
Right, very good. So let's see this. So suppose we are taking only one two input AND gates, right? So here it is x and it is y. It is x and z, right? So this output would be xy. This output would be xz, right? Now we can take this two and connect it with an OR gate, and we can get this f, right? Okay. Similarly, if you have to suppose get another function, say any arbitrary function, say x, y plus z into say a, say, okay, then or here this x, y is also in smaller letters. So here let me write in w. Okay, so x, y plus z w. So can you guide me how can I do it?
Sir, X, Y, and Z,
Okay, so it
Z
is
means
x, so it is x, y. Okay,
then one Z
okay,
and
so
then
one z
or
means it is
or
OR gate, right? It is
yes
then
sir.
OR gate with this. So it
And this
becomes x,
whole
y
W
plus
with
z.
yes sir, and it will with and
It is with and with
W.
w, right? So that way, this is and that way you can actually implement this circuit using this basic gates, right? So here, this is like one, this one expression, right? And this Boolean algebra is used to minimize this expression. Okay, but unfortunately this equation cannot be minimized because this is the actually the minimum form actually, right? But I will show you after this that the several in different cases you can actually reduce that expression that is given to you, right? So when you can reduce this expression, what will happen? You need less number of gates to implement that particular digital function. Okay, so let us first learn this, and then we'll see. So for Boolean algebra, so couple of I think postulates we should learn first. So first one is this x plus 0. So x is like a variable which can take this is basically an binary variable. So it can take either 0, it can be 0, or it can be 1, right? So that way. 1 means, again remember that 1 means not the value 1. It is basically the digital logic 1, right? It is basically a voltage which is maybe it is either 5 volt logic 1 if the VDD is or VCC is equal to 5 volt, or it may be 3 volt, it may be 2 volt, depending on the value of VCC or VDD, right? So x plus 0, right? So when you like do an odd operation between x and 0, so basically then the result would be dependent on the value of this x. If it is 0, then the output would be 0. If it is 1, x value, output would be 1. So it is basically dependent on x. Okay. Then see x plus x bar. Right. Okay. What will be the result in here? Result here. So it is x plus x bar. See, if it is x is 0, right, then x bar would be 1. So 0 plus 1 would be 1, right? Because it is an odd operation. Similarly, if it is x is 1, then it is 1 plus x bar becomes 0. So 1 plus 0, odd operation. If either of if one of them is 1, then the output would become 1. So this x plus x bar would become 1, right? Then x plus x, remember here, it is not 2x, right? Because it is an odd operation, right? So if it is 0 plus 0, so it depends on what is the value of this x. If it is 0 plus 0, then the output would be 0. If it is 1 plus 1, then the output would be 1. So basically x plus x is equal to x, right? Okay. Then see x plus 1, right? X plus 1 is, it is x is 1, x maybe suppose 0, then also the output would become 1. If it is x is 1, then also output become 1, because OR operation, this is on, right? If this is on, then it does not matter what is the value here. Okay. Then x bar, whole bar, x bar, then one more bar, right? So when you take x bar, so that means suppose x is 0, then x bar become 1, right? Then again you are taking a bar, the one bar becomes 0. So is basically equal to x, right? Anything you take 2 times bar, then it becomes that that variable only, right? Similarly, this is quite basic. X plus y would be equal to y plus x, right? Then x plus y plus z, y plus z, this would be equal to this associative and all this type of properties, right? With the basic properties, right? Just you can write it like this. Then suppose x, y plus z, right? It would be xy plus xz. Okay. So here, these are the couple of couple of postulates, and here is one theorem. This theorem is called this De Morgan's theorem. Okay, maybe before the De Morgan's theorem, I will show one more. Right, one more here. That is this one. See this x plus xy. Right. So what will be the value of this x plus xy? See, this will be equal to x only, because it is not difficult to understand. See, you can take x common from here, right? So it become 1 plus y, right? So see this, anything plus y means y plus 1, right? You can see here this x plus 1 would be always 1, right? So that means this is y dot 1, so which is nothing but x. So you can see this is quite simple. So x plus xy would be equal to x, right? Okay, now let us see what is this De Morgan's theorem. So De Morgan's theorem says that if it is x plus y and you take a like, okay, let me write it clearly. So x plus y, right? And if you are taking a whole bar of this, right, means you are taking an invert of this, then it would become x bar dot y bar, right? It is called De Morgan's theorem, right? Okay. So here you can see here more OR operations, right? Here this plus 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 mostly or this OR operations. Now similarly, we can also write similar things for AND operations, right? For example, this x dot 1, right? So anything you multiply with 1, right? This may not multiply actually, it is basically AND operation with 1, right? That depends on the value of this x only, right? Because if this x is 1, then only 1 dot 1 become 1. If this x is 0, then the output would become 0 only, right? So it is basically x. Then x dot x bar, here is something interesting. See, if this x is 0, right? If this x is 0, x bar become 1. So 0 dot 1 becomes 0, right? If this x is 1, x bar becomes 0, right? So whatever you will take, the output will always come to be equal to 0. Then x dot x, right? X dot x would become x only, right? Because it is 1 dot 1 become 1, 0 dot 0 becomes 0. Okay. X dot 0. So x dot 0, it is always 0, right? Because one of the for AND, if one of the input is 0, then definitely the output is 0. Similarly, y can be written as yx, right? I mean, it does not matter which one you are writing it first. Then x yz, this can be written as xyz. Then here x plus yz can be written as x plus y and x plus z, right? So you can actually easily do, you can actually check it, right, whether you can write it or not. So would you like to check it? Who can, okay, can you please check it from whatever you have learned? Can you please confirm that whether this whatever I am writing is, whether it holds or not?
Yes, correct.
Is correct, right? Okay.
Yes.
Okay. So then this xy, okay, I think I will write the De Morgan's a bit later on.
Sir, I
So
didn't.
what? Hmm?
Sir, I didn't get this last part, sir.
And
Like,
this last one,
yes,
this
sir.
one.
The remaining,
Okay.
yes,
Right, right. So one of your friend has got. So could you please tell us like how have you
Sure.
proved this?
X in x and x plus x and z plus y and x plus y and z.
So it will, so basically you are multiplying it, right?
Yes, means we can do the
Okay, so
distance.
it become x dot x become x, or this become xz, this become xy, this become zy.
YZ. Yes,
Then
sir.
take x
Right,
common.
yz, zy. Okay. Then,
X and 1 or z or y.
sorry, x
X and 1 or
and
z or y.
1
Or z or y. Means 1
1
or
plus
plus
1
z,
x
plus.
plus y.
or z. Oh, right, right.
Then we can
Okay.
Okay.
write this as
Got
1 only.
So it is 1 plus anything, this odd operation that will become 1 plus yz. So that would give you x plus yz. Right. So it is in this way you can check it like whether this is the same or not, right? Okay. So here in this context, there is one more De Morgan's theorem, which is type of this multiplication. And then if you take and like inverse of this or make a not operation for this, then it will become x bar plus y bar. Fine. So this is important De Morgan's theorem. Huh? Then here this x into x plus y, that is equal to x. Can you please check whether you have understood this or whether this will hold or not?
Yes, sir, it will hold.
Yes, sir. It
It will hold, right?
will
Okay.
hold.
Okay, then. So we have understood the postulates and we have an idea like now how means this digital operations we can actually means if there is something like x plus 0 we can directly write x, right? This type of manipulations now we will be able to do it very quickly, right? Okay. Now let us see one thing. Hmm. Right. Okay. Now probably we will take some examples and okay, here I think one more thing is important to mention is this operator precedence, right? Mm. So operator precedence would be first, it is this parenthesis or the bracket you have to means operate. Then it would be the not. Then the third one it would be and the fourth one it would be or. So what does it mean? Means suppose in a function you have like all this, you have this bracket, right? Then you have this not operations, right? Then you have suppose this or operations, then you have some and operations, right? And operation between these two. Then which one, which operator you should you should evaluate first, right? So the first one would be this, second one is this, third one is this, fourth one is this. Okay, then probably we can go to the next page and let us see some of the examples that how we can do all these things. Okay, so let us take some easy examples only. So let us say some function f is equal to x plus x plus x bar y. Okay, this x plus x bar y. Now, the thing is that let us see that here. Okay, first the thing is that this is the function, right? So let us implement the function using different gates. So let us try to do that. Okay, so it is we have input x, right? Because we need this input x as well as this x bar, right? So we have this x. Then we can use one NOT gate to make this x bar, right? Do with this x bar now we can use an AND gate, right, to get this x bar y, right? And with this we can use an OR gate, and here this is the x, right? We can use this is so this is x and this is this, so it become x bar y, right? So this is the way we by which no, this would be one more, right? It is plus x, so this is the function. So this is one of the way by which you can do it. The circuit you can implement. Okay. Now let's see that can we do something to this expression based on whatever the Boolean algebra or the postulates that what we have learned. Okay. So let us use this postulate here. Okay. This one. This postulates x plus yz equal to x plus y into x plus z. Okay. So let us use this. So it is x plus, remember this is yz, right? So it become x plus x bar, then x plus y, right? Okay. Now what is x plus x dash? Guys, please tell me what is x plus x dash?
1.
1. And this is x plus y, right? One operation with another function. This would give us 1 and this. Output would be
This, sir, x plus y.
x plus y, right? So you see the same function can also be represented in this way, right? Now if we want to implement this using this digital gates, then we need only one gate, only one OR gate, right? So here what we have learned, see this function and this function, they are same, right? But here why you will making this implementing this using this technique, so you need number one, how many gates? 1, 2, 3 gates, right? Here how many gates you need? You need only one gates, right? Here you need 3 gates, here 1 gate, right? So see the same thing, right? But what is the difference? Here we have implemented it directly, here we have tried to minimize it, the expression, and then implement it. But what is the result? Here, drastically the number of gates, the use of number of gates that has been reduced. When you do that, for every gate there will be some power consumption. You reduce the power consumption. For every gate there will be some delay, right? When you give some input, this output will not immediately come here. There will be some delay, right? Then from here to here there will be some delay. Then from here to here there will be some delay. So so here it is, if you consider like all gates have similar delay, then the delay is of 3 units. Whereas for this case, in this type of implementation, the second implementation, delay is only 1 unit, right? So less number of gates, means less power dissipation, right? Less delay, right? So all these are important for circuit design. So I think then you have understood what is the importance of minimizing the Boolean expression that has been given, right? Okay. So now let us take one more example and let us see what can we do with this. Here the function is given as xy plus x bar z plus yz. Right now we have been asked to minimize this, or is it possible to minimize this? The answer is yes. So let me do it, and you please see that how I am doing it. So we are just keeping these two as same, and this yz we can write it as yz dot one, right? We can always put dot one with any one of them. So we are writing here dot one, right? This one can be written as x plus x bar, right? You know that, right? All the postulates we have learned. X plus x bar equal to 1. So now we can write this 1 as x plus x bar, right? So that makes this x bar z, then xyz plus x bar yz, right? Okay. Now we will take something common from this. So let us take see this term and this term, okay? And let us take xy common from this. So when you take xy common from this, it becomes 1 plus z, right? And let us now see this term and this term, okay? And let us take this part common, right? X bar z. So when you take x bar z, it is 1 plus y, right? Okay. Now you see x dot y, 1 plus anything, that would become result become 1, right? X bar z, 1 plus y anything become 1, right? So multiplying means basically this add operation with 1 basically gives you the same. This here also AND operation with 1, that would result in this, right? So here what you can see from this is a bit surprising. See this here, this is the total term, right? But here you see this is the term, and if you notice bit more carefully, you see the first two terms are enough to represent this function, right? So the third term is of no use. So if you want to implement this directly using these gates, then here you need uh, another what type of gate, another AND gate, right? But it is not required actually if we can minimize it. So that way you can see this, you know, how important it is to if to do a proper minimization of this any digital function, means any Boolean function, right?
Hello, sir.
Hmm.
Sir, why did you put that one of the last as x plus x bar? Like we can do this thing in any of the terms, no, sir?
Yes, yes, that comes with a bit practice, right? If you do it with the other one, you will be it will be difficult for you to get this minimized expression. Okay, because
So,
what you are asking, okay, I understood. See here, first thing is that why we are doing it here one, because then from this term, the term that we will be getting is that x y z, right? I'm just in my mind I am doing it, okay, and it is x bar y z. Then I can see from here this is x y. Here this x y term is there, so it become 1 plus z, and for this it is x bar z. So here is x bar z, and if you take this common, it become 1 plus y, right? So that is why this term is being introduced here. One. Is that clear to you?
Sir,
Hmm.
sir, how can we be sure that we cannot reduce it further from here?
Yeah. So please try this and let me know if you can reduce it
yes,
any
sir.
further
Can
from
be
here.
xy plus z.
X, y plus z.
Yes.
X, y plus z.
Yes.
Okay. How? Please
Sir,
explain.
we apply that property that x plus yz is x plus y x plus z.
Okay. Let me write it. So you saying that here we can write it at x, y plus x bar.
Yes, xy plus x bar into xy
Okay.
plus z.
Into, right? X, y
Uh,
plus z. Okay.
and left side will become 1.
So this left side.
Yes.
How?
Again using that property, sir. X plus
Okay,
x.
again we want to use this property. Okay, so let us do that. So again it is, so how we want to split it now? It would become x bar plus x, right? This is now A, this is BC. So it become A plus B, then it become A plus B, then this term, right? So
Oh,
you see this term is becoming 1, but you are left with this term, right?
actually, sir, if we start by taking z common, then I am getting xy plus z, sir.
If you are taking
From the
Z
first
as,
step, we take z common.
Z common between whom? Between these two.
XYZ and YZ.
Okay, so let's do that then. Hmm. So, okay, you are suggesting that we will take Z as common, then we will get Y plus X bar, right? Isn't it? Hello.
Yes, sir. Yes, sir.
So you were suggesting this. Okay, next.
Sir, then we take um just a second. Okay, I made a mistake. Sorry, sir. Yes, I
Okay,
made a mistake.
right. So the thing is that okay, I am not you asked an important question. I think did I miss something here? Okay, no. So I think here something was there, no? This X bar Z. I think for that Z this was missing. Okay, right. So here the one of you have asked like how we are so sure that it cannot be minimized further. No, we are not sure. So you can try it. So if you can still minimize it, right? So from this using this boolean this this boolean minimization technique, it will be difficult to really comment on that, right? That what we have achieved is minimized one or not, right? So for that there is one technique which is called the Carnot map technique. By using that technique it would be a bit more easier for you, like it would be easier for you, that okay, this is the minimized form of the expression. Okay, but here like you have to do after that also do some trial and error and see that whether it is really you can minimize it or not. Okay, so I think yeah, this is mostly regarding this minimization part and how much time I have. Okay, so probably I can start this one. So here this the couple of things we need to learn. This is standard forms. Okay, 1 minute. Algebraic manipulation. Huh. This is standard forms, right? So standard form means this any function, right? So probably suppose in any function I can write in this fashion, right? Say any arbitrary function I can write it like this, or yeah. So I can write it like this, right? Or oh maybe like this, or maybe some other function. Okay, so it is f1. I can also write like this, no? X plus y, then y plus z. Right? These two are different functions, but I can represent them in this way, right? So here you can see each term is been first anded, then it has been ORed, right? This and like each term is been first and operation between them, and then finally we have ORed, or the means summed up, right, between them. But here see this process is the different. Here inside this every term is first like type of OR operation, and then different that all these terms inside they have been and this and operation has been done between them, right? So based on this, like how we can represent a function, there are two ways by which we can do it. One is called this min term. The other one is called max term. Okay. So to be quick, when you are doing it in this fashion, right? Like x y plus x dash means first and then or, right, between them. Then this is called this min terms, right? And when you do it like this, first or and then and operation between them, then it is called this max terms. Okay. So let us take an example and see it in a bit more detail. So let us say that we have two variables. I think I could have done here one more thing. Okay, probably I will try to do it here first. Then I will move to the next part. That part, okay, that would be helpful. So let us take this example. Okay. No, not this. So let us take this example only. Okay, F. So say this f is equal to, finally what we have seen is this x bar z, right? Then if I ask you, can you make a truth table of this function? Can you make a truth table for this function? If yes, how can you?
Sir, we
Using
can
eight
just
values.
Huh?
So like using the values of x, y, and z.
Very good. So first, for truth table, so here clearly there are three inputs x, y, z. So write three inputs. Here we have this function, right? Okay. So it is 0, 0. So you have to first write all these 8 possible combinations between them, and then you have to proceed. 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. See this all possible 8 combinations we have written between these three inputs, right? And this is the output, right? And let's see that. So when this see this xy, right? So for this, let us take this x 0, y 0, z 0. So xy 0, 0. So this is 0. Then x bar is, this is 0. So x bar become 1, but z becomes 0, right? So this becomes 0, right? Okay, let's take the next one. 0, 0. So first one is 0. Second one is x bar. X bar become 1, and then z. Z is here 1. So it is 1 dot 1. So the output is, and this one, this become 1. So it is 0 plus 1. Output become 1. Let's see this third one. 0, 1, 0. So it is 0, 1. 0 dot 1. Output 0. Right? This part is 0. The next one is x bar, that is 1, right? But z is 0. So this is 0. So here this is 0. The fourth one, 0, 1, 1. So x 0, then we should not see what is the value of y, because definitely then this term is 0, right? What about the next term? X 0. So x bar become 1. What about z? Z is here 1. So this output become 1, right? Then see the sixth term. 1, 0, 0. So x is 1, but definitely y is 0. So this is 0. X is 1, right? So this x bar becomes 0. So you should not see what is the value of z. Definitely it become 0. Then we'll see this one. So you have understood. I think let us not do it again. That this process you can use, and you can make the truth table, okay, from this expression, right? Okay.
Sir,
So yes, you have a question?
yes, sir, that is xy plus z, sir. I sent a proof in the chat box.
Proof in the chat box.
Yes, sir. Means I sent a image. It is xy plus z, sir. I did it on paper and tried.
Okay, okay. So let us check it, or maybe your friends. Okay, maybe then all of you can refer to the chat window that your friend has shared. So what you have done, x plus xz, this it is xy plus this xz. What you were writing here, xy plus this term, and then xy plus xz. Okay, and then what you are doing, you are taking these two terms plus xy plus z. Then you have taken this y as a common. Then it is 1 plus y plus xz, xy plus z. So it is x plus x bar. So this become 1. And this is xy plus this xy plus z, and this xy plus z. Okay, so can you also do this? Okay, I have
So in the
done that.
fourth line there
sir,
is
in the
error.
fourth line.
Just taken
Fourth
y
line there is
common.
an error. Okay, what is the
Ah,
error?
I took x instead of x. I took y common. Yes. Instead of y, I took x. Yes.
So okay,
So
okay,
then
then please correct that, huh? Okay, so let us then come back and see this standard form. Okay, we have. Oh, I think we do not have time. It's almost 11. Do you have a class after this, or can we take a few more minutes?
We
Sir,
have
we
class.
have a
Yes, sir,
class.
we have a class.
A class. Okay, no issue. So we will continue from here in the next class. Okay.
Thank you, sir.
Okay
Thank
then.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, you are welcome.